you've heard of the Big Bang? Good, thanks, I'm glad to hear that. The guy who named it was a man named Fred Hoyle. He's an English astronomer. He did it derisively. Like a lot of the most famous names in history were originally insults, like Gothic or, well, the Big Bang. Anyway, it turns out the Big Bang is right. Hubble was wrong, Hoyle was wrong, but he's the one that gave it that name. Now, we're ready to look at particle physics. Something that everybody just can't wait to do. And it would never, ever fill anybody with fear and loathing. But I thought you'd feel better if you looked at that face. That's Max Planck. He's the father of the quantum physics. In 1901, he wrote a paper and he said, okay, get this. Everything is fundamentally uncertain. And there's nothing you can know for sure. But with energy is emitted and absorbed as discrete quanta. Now that's an exciting sentence, right? So I'll say it again. Energy is absorbed and emitted in discrete quanta. I mean, I don't know how you can contain your excitement, but that is a really important statement, you know, even though you don't realize it. If you're someone like Einstein, you realize it, but if you're someone like me, it takes a while, right? But the idea here is that it used to be thought that energy could be emitted over any spectrum, but it turns out that it can't. When things get really hot and really small, it's only absorbed as quanta. So what a quantum is, singular quantum, plural quantum, a quantum is just the smallest measure of anything that you can have in a given system. So in a system like an electron, like an atom, okay, you got an atom, you got your nucleus, your electron. In a system like that, energy, which is distributed through the electrons, I'll explain this in a second, it sounds horrible, but energy is only emitted and destroyed in little chunks. That's what I'm trying to tell you. It's absorbed and emitted in little chunks. Einstein comes along 4 years later, and writes a paper called the photoelectric effect, which again, sounds really exciting. He shows that that photons can knock electrons off metals. Big deal, you say. Well, it so happens that again, it's done as quanta. So Planck started talking about how energy is transmitted in quanta. Einstein said, yeah, not only that, but light itself is transmitted as quanta. So what does that make light? It makes it a piece of something. It makes it a chunk, just like Newton said. He said it was a chunk called a corpuscle. These guys all said it was waves. Now, Einstein, the second greatest scientist in history, is saying it's particles. So what is it? Well, in a minute, we'll get down to this guy. But first, let's just back up for a second and look at one of the pioneers, Ernest Rutherford. The reason I want to look at this guy, oh, that's not him. There he is. He worked in Canada for a number of years at McGill. And he did some really important work with another guy called Niels Bohr on developing atomic theory. So I just want you to know that we had a special chair which we created for him in physics at McGill University, back around the turn of the century. And he worked with another guy whose name is Niels Bohr, number 32. Oh, Rutherford discovered something that's really important. Again, may not sound that exciting, but super important. He discovered that radioactive elements have a half-life. So if I'm a uranium atom, say I'm a uranium-235 atom, that would give me a half-life of 700 million years, 710 million years. What does that mean? That means that in 710 million years, half of my uranium has turned into lead. I looked it up, and all of the lead in the world, except for a little tiny bit called lead-204, was originally uranium. All the lead was uranium. And it's all decayed from uranium to lead. If it's uranium-238, which is the less radioactive kind, the half-life is 4.46 billion years. It's the same age as the Earth. But if it's the other kind of uranium, it's got a half-life of 700 million years. So, do you understand now? If you know something's got a half-life, and that enables you to tell how old it is. If there's half of it left, it's that age. If half of that's gone, it's that age. When half of that's gone, it's younger still, right? It's beautiful. It's beautiful. It's just lovely. So, sorry, I shouldn't tell you how to feel. So, you got Rutherford, who discovered the half-life, and he discovered beta decay. So you're thinking, who cares? Beta decay, hon. It's my big moment. The prop.
It's behind you.
It's behind me.
Look behind you,
Behind me.
on the board.
Oh! Isn't that something? This, as you probably figured out, is a banana. And why would I be talking about it when I'm trying to talk about a guy about Niels Bohr, right? I mean, it's boring enough. But this banana, I'm talking about beta decay, okay, and Rutherford discovered it. Beta decay is going on in the sun and the banana. So think of yellow up there in the sun. That sun, right now, is turning 600 million tons of hydrogen into 594.5 million tons of helium. And the only way that that can happen is if a proton can turn into a neutron. And that's what happens in beta decay. And that's what happens in this banana. You'd have to eat 1,000 of these every day to get as much radioactivity as you would just going in for an X-ray. I mean, I think you have to eat more. No, the bananas are totally harmless. But there's beta decay going on in here as we speak. Neutrons are changing in. No, I think there's two types of beta decay, positive and negative. One of them gives you an electron and a neutrino, and the other one gives you an antineutrino and an anti-electron. I can't remember which kind is going on, but it's beta decay. And it's the same process that lets the sun shine. The first step in the sun shining in nuclear fusion is the changing of a proton into a neutron. Okay, so we're talking about whether light is a matter or a particle. Let's have de Broglie. This guy looks like an artist, but he's actually a physicist. Number 33. Thanks, son. De Broglie said, okay, this is what the deal is. Light is a matter wave. It's a wave, it's matter, it's a matter wave. Light is both a particle and a wave, okay? Fine. Now, that was in 1924. In the same year, this guy, number 34, quite a name, Satyendra Nath Bose, wrote a letter to Albert Einstein. He said, hi, you don't know me? I'm a physicist over here in India. And I was just looking at Max Planck's derivation of black body radiation. And I think I figured out a new statistical way of interpreting that. So I've got 5 pages of equations here that I've enclosed. And I'm thinking, if you think this is any good, could you please translate it into German for me and present it? He said, like, me and my buddies over here, we've been learning German and French and English because we've been studying what you guys are doing over in England. But they won't publish me because I'm a nobody. So Einstein looked at it, and he, you know, being Einstein, A, caring about science more than ego, which I like, and B, realizing that there was something deeper here, saying, sure, I'll do it. So we presented it, and Bose became an internationally renowned physicist overnight because of Albert Einstein. Bose and Einstein collaborated for the next 2 years, mostly by letter, and in the end of it, in 1926, they came up with a prediction that if you made a certain kind of matter cold enough, that all the individual bits of that matter would behave as one. That is called the Bose-Einstein condensate, which is as exciting as its name. And in 1995, people finally discovered one. Isn't that cool? So 1926 to 1925. Bose and Einstein, I love it. What I like about Bose is that even though he was a world-famous physicist, in India, what did he do in his spare time? He organized working men's clubs and went out and gave lectures on nuclear physicists to guys who worked for a living. I really like that. Just the idea of taking knowledge and spreading it around. I gotta admit, I'm a sucker for that. I think that's the best thing. So back to Lemaitre, number 35, the guy who started it in a way. So he was looking at Einstein's equations on relativity. Oh, by the way, I really should mention a couple of things about Einstein. Let's look at Einstein and that. That's it? Okay, good. Einstein took Newton's theory of gravity and he said, well, that is a great theory, and it's been just fantastic for 200 years. First rate. He loved Maxwell's equations too. He was studying those extensively as a young man. But he said, unfortunately, what gravity really is a warp in space-time. Space and time are a fabric, said Einstein. They pervade the universe, and what gravity is, it's mass bending space-time. Newton said it's an invisible attraction between two objects, right, or two or more. Einstein said no. What's happening is that a heavy object like an apple or the earth or the sun makes a dent in space-time, and other objects come along and they'll rotate around it, and they'll keep rotating if there's enough angular momentum, and if there isn't, they'll go right into it. So that's what gravity is, according to Einstein. And everybody accepts that now, but we still think of it as an attraction between forces. Like when I'm trying to hike up some stupid hill, I don't feel like I'm warping space-time. I just feel like something's got a hold of my feet. And it's, you know, come on feet, don't fail me now. You ever hear those? Yeah, me too. I used to have dreams like that. They were in cement. Yeah, so Lee Mattray then in 1931 put out another paper on how the universe was expanding, and this time people were ready to hear it. Okay, we're just about at the end now. You get to the light at the end of the tunnel, because that's what we're talking about. We're showing how light was thought to be a particle, light was thought to be a wave, then it's a particle. Well, you know what we know now? It can act as either. If you put it through a double slit experiment, it'll show up as a wave. But get this, if you think, okay, light, I'll trick you. I'll plug up one of those slits. It still does the same thing. Go figure. Give it one slit, it seems to separate, go around and interfere with itself. It is just weird. And then in other circumstances, it acts like a particle. But it's not matter, because matter has mass and takes up space, and light doesn't. Finally, Heisenberg and Schrodinger. You've heard the names probably, right? Anybody watch Breaking Bad? Woo! Remember Heisenberg? I don't know why I called him that, but there was a real Heisenberg, and I can put in a nutshell why you should care about Heisenberg. This is what he said. Heisenberg said you can know where something is, or you can know how fast it's going, but you can't know both. Isn't that weird? So, under Newton's law, if I'm heading to Kamloops and it's 100 kilometers and I'm doing 100 kilometers an hour, you know that in half an hour I'll be halfway there, and in 1 hour I'll be there, right? Long McQuaid phoned up, said your new guitar's in, and I'm there. Heisenberg said, okay, under Newton's way of thinking, you can know exactly where L is. But if L becomes a photon, or an electron, or a proton, or some subatomic particle, you can't know where L is anymore, because he has now become a cloud of probabilities. That's what happens. In the quantum world, there's no such thing as knowing exactly where something is and knowing how fast it's going. All you can do is create an equation that will give you the probability of finding L. And when you look for him, if you find him, great. If you don't, you got to start the whole thing all over again. He could be anywhere between there and there. It's just probabilities. Schrodinger to the rescue. Schrodinger comes along, 1925, same year. Yeah, there he is. He brings in this thing. This is called psi, PSI. That's a Greek symbol, and that is a wave function. And Schrodinger said, okay, that equation represents everything you could know about a quantum system. All that means a really small system like an atom. Quantum, it just means what's the charge, what's the spin, how fast it's going, where is it, anything you want to know. You can figure out if you know how to do these equations, and if you're really smart, which I'm not and can't. But you take that psi, which is a symbol, that's your wave function, and if you square the modulus of it, you can get the amplitude of the probability density of finding an electron somewhere between here and Kamloops. That's what the Schrodinger equation lets you do. It takes some of the uncertainty out of the fact that at a very small level, everything in the universe is uncertain. Yeah, I know, I don't blame some of you, but you're holding up really well. And our last guy is Paul Dirac. Paul Dirac was a nice guy. He figured that Satyendranath Bose never got a Nobel, despite all the important work he did. So he called the boson after Bose, and that's why we call them bosons. So where are we then looking at our little universe atomically and bosonically? Know this, there are two types of particles. There's one kind that regular matter is made out of, and those particles behave just like particles should. If you take them to a hotel, they all get their own rooms and everybody's good. But there's another kind of particle called a boson. Bosons don't obey the same law. What's Pauli? Can we show Pauli? Is he number 31? I can't remember. I don't think he is, no. 39. Wolfgang Pauli came up with the Pauli exclusion principle, and he told you what I'm just telling you right now. He said there's a type of particle where you can only put one in one place at one time. There's another particle where you can put as many as you want in the same place at the same time, believe it or not. And the ones that go in the same place at the same time are called bosons. And the ones that don't are called fermions. You don't have to know that. Just know there's these two different kind of particles. And why we care about bosons is the photon is the boson that makes electromagnetism work. So the next time you turn something on or off, it's your photons in there. They're the force that is making your electromagnetic force work. Gravity-wise, we don't know. It's a complete mystery. Nobody's found a gravitron. But the other two forces are called the strong force and the weak force. And the strong force is what holds the nucleus together. It holds the protons together. And the other force is the weak force. And that's the one that lets the banana and the sun operate. So those are the four forces of nature. And you've got two main kinds of particles, the kind that make up atoms and the kind that make atoms work. So you've got your bosons and your other particles. I hope that's okay. I mean, it makes sense to me, but everything makes sense once you know it, right? I'm not very good at learning a whole bunch of stuff at once. I'm not. I'm serious. I mean, I need a break. It's all I do, but I do need a break, and I find that I just can only take so much at once. So I apologize to you. I'm probably throwing a lot of terms at you, but I wanted to show you the people that did the science as well as the science, all right? So now we've looked at the people. I've got 15 minutes exactly to do the Big Bang. And it should be done in 15 minutes or less because you guys are tired. I've really put it to you, haven't I? Hey, this has been non-stop. Please come back. Okay, in the Big Bang, that's 10 to the minus 43. Everything's squished into one place. What's going to happen is gravity liberates itself. We undergo a phase transition. What's that? A phase transition is where you got water in your stove. You turn it on, it boils. Water's going from a liquid to a gas. That's a phase transition. Why do you care? Because it releases energy. What's the big deal about that? Because the universe is all about energy. Life is all about energy. Everything is about energy. Life is a competition that's played out in various different ways, cooperatively, parasitically, all sorts of different ways to get energy. So everything in the universe is trying to get energy and conserve it. It's a law. It's called the conservation of energy. And the reason I'm mentioning it is that a huge amount of energy is released every time there's a phase transition. So energy, universe starts to blow up. We're going to need balloons in a minute.
Balloons.
Hey Claire, this is it.
It's party
I'm going to
time.
do a prop thing here, right? Should have done this earlier, but we'll do it right now. What happens is the universe blows up. And remember I mentioned there were little clumps? That's the last thing I mentioned. I said, okay, clumps, then we're going to go on to the people. Okay, so when the universe was all mashed together in a tiny little place, everything was in little clumps. Well, as it expanded, those clumps got bigger. Now what we've done is we got some balloons, and these are Canadian balloons, as they should be. We're going to push Canada as much as we possibly can. Now what Denise has done is she took these balloons, every one of these is one of those original clumps. Remember how tiny it was?